Welcome back. This is our first video lecture for material in Chapter 4 of Fundamentals of Physics. Chapter 4 is titled Motion in 2 and 3 Dimensions. So the big picture for the chapter is we're going to really basically combine ideas from Chapters 2 and 3. In Chapter 2, we studied motion in 1 dimension, along a line, and we introduced the concepts, the key ones for kinematics describing motion, are position, displacement, velocity, and acceleration. Okay? Those 4 things. Now we're just going to acknowledge the fact that particles, objects, can move around in more than 1 dimension. You can have 2-dimensional motion on a flat surface or on a surface, or you can have 3-dimensional motion, where you need a 3-dimensional coordinate system to describe the motion, right? I mean, that is what is more likely in the real world. So we need to take the ideas from Chapter 2. We're not going to define anything new. We're just going to apply the concepts from Chapter 2, position, displacement, velocity, acceleration, to motion in 2 and 3 dimensions. To do that extension into 2 and 3 dimensions, we need full-blown vectors. And we have to understand vector algebra and be able to manipulate vectors correctly, and that's why we need Chapter 3. So Chapter 4 is really just combining Chapters 2 and 3. And as I said, as you're going to see, we're not going to define any new quantities in this chapter. We're going to just work with position, displacement, velocity, acceleration. However, the math is a little more complicated because now we're looking at motion in 2 and 3 dimensions, not just in 1 dimension. Okay, this lecture is focusing specifically on Chapter 4, Section 1, position and displacement, and Chapter 4, Section 2, average velocity and instantaneous velocity. And please remember, if you want more content, you can read those specific sections in Chapter 4 when you go to Wiley+. I am giving you a summary and my own emphasis of the important ideas from those 2 sections. Okay, let's get started. We're just going to remind you of some definitions from Chapter 2, starting with position. Okay? Now let me start by working in just 2 spatial dimensions. So now we're going to imagine an object is moving around on a flat 2-dimensional surface, and we're going to use an XY coordinate system to describe the motion. Okay? So we're going to start with position, 2-dimensional version, and you can be looking at the picture I have right here, which is an XY coordinate system. And in this picture, I have drawn a sketch of a particle's path. So if you want to imagine a specific scenario, let's imagine that you are hovering in a big balloon above a flat field, or maybe a flat parking lot. And you're looking down on this flat field or parking lot from above. And surprise, surprise, somebody has painted an XY coordinate system. Painted an x-axis pointing to the right and a y-axis pointing up on the flat surface. And of course, where the x and y axes cross, right there in this drawing, is the origin O of our coordinate system. Okay, and in this coordinate system, as we are hovering in our balloon looking down from above, there is some particle moving around. Maybe it's a squirrel moving around, scampering around on the ground, doing its thing. And the actual path the squirrel makes is this brown curve that you see drawn in the XY coordinate system. And it's marked there. It says particle's path in the XY plane. Okay? Such a path is also called, by the way, its trajectory. Okay, so that's what the particle, the squirrel, that's the path it's moving on. Suppose at one moment in time we could take a snapshot, flash, freeze, and see where the squirrel, the particle, is. Okay? And our picture shows it right there. You can see the dot that shows the particle. Here comes our definition of position vector, 2-dimensional case. The position vector of the particle at any given time is a vector that points from the origin to the particle's location at that instant in time. That's it. By definition, the position vector points from the origin to the particle's location. So it's drawn there, but I'll draw over it just to be clear. You go from the origin out to where the particle is located. That's drawn there as a blue arrow. Please note the notation we're going to use for position vector. From now on, R arrow, okay? And that's how it's labeled in the picture if you look very carefully. Right above that blue arrow, there's an R with an arrow over it. That's the position vector for our particle at this instant. Now, this particle is at some point, this squirrel is at some point in the xy plane. And you probably are used to denoting a point in an xy plane by giving the x and y coordinates as an ordered pair, x comma y, for that point right there. And they're also drawn as components because the xy coordinates of that point in the xy plane are also telling you the x and y scalar components of the position vector. You can see them drawn here. See the arrow along x? Labeled x, I'll draw it bigger. That's the x scalar component of the position vector. You see the arrow drawn here, labeled y? That's the y scalar component of the position vector. It's telling you where the object is located, right? Relative to the origin. Now, to get used to representing the position vector in unit vector notation, look over here that I just highlighted here, that expression in yellow. I'll underline it too. We will often write the position vector R arrow in unit vector notation. That means simply take the x coordinate of its position and multiply that by I hat, plus the y coordinate multiplied by j hat. And you've denoted then the position vector in unit vector notation. These are all equivalent ways of denoting where the particle is. Okay? Now, probably the particle is moving, right? If this is a squirrel, you rarely see a squirrel at rest. They're always scampering around. So if we look a little bit later at a different time, the position vector will have changed. So, just like in chapter 2, we can define displacement. And we can define it as the change in the position during a specified time interval. Now I want to draw my own part of the picture here on the screen. Let me draw the xy coordinate system just as before, x and y. Okay? And let me draw the trajectory. Oh, I'll draw it in purple. Say it's something like that. That's the path that the squirrel is going to run along. And let me draw the squirrel's position at 2 times. Let's say at time t1, it's right there. Time t1. The squirrel is located right there. And let's say those coordinates at time t1 are x1, comma y1. And now let me draw the position vector at time t1. That would point from the origin O out to where the squirrel is located. And let me label that vector R1 arrow. There we have position vector at time t1. Now, let's wait a little bit. A little bit later, let's call time t2. Let's say the squirrel has moved along its path and is now right there. Okay? So that's the location of the squirrel at time t2. And let's say its coordinates are x2, comma y2. And now let's draw the position vector for time t2. Straight out from the origin to the point 2. Label it R2 arrow. I must emphasize very strongly how you've got to draw the arrow symbols over vectors now. From now on, we have to do that so that we keep reminding ourselves, well, that's right, this quantity is a vector and it's got components. All right, so you can see in my new drawing that the squirrel's position vector has changed from R1 to R2. And so there is a displacement for this squirrel. And I want to now talk about how you figure that out. Note, I have it here on the screen, the way we're going to denote displacement, which is change in position, is delta R arrow, right? Change in position vector. That's what displacement vector means. And, as always, change of a quantity means final value minus initial value. So change in position vector means the final position vector minus the initial position vector. R2 arrow minus R1 arrow. And we must be very, very careful because this is subtraction of two vectors, okay, in two dimensions. So you've got to deal with components. In fact, let me show you now how you do the subtraction dealing with components. It's really quite easy for displacement. Remember, we know x1, y1, and x2, y2. The x and y coordinates of the squirrel at time 1 and time 2. So to calculate r2 minus r1, okay, here's all we do. We take x2 minus x1 and multiply that by I hat, and with the unit vector I hat, then plus y2 minus y1 and multiply that by j hat. You'll see your book writing this as follows. x2 minus x1, it's just a change in x, so they'll call that delta x times I hat. And y2 minus y1 is the change in y, so they'll denote that delta y. So delta y times j hat. And that's, of course, if you look here, the expression I have on the screen. Delta r arrow equals delta x times I hat plus delta y times j hat. And that's how you calculate delta r, the displacement. You have to know how much the x-coordinate changed and how much the y-coordinate changed. And then you just take delta x times I hat plus delta y times j hat. And you have computed, analytically, delta r vector. Now, what does delta r vector look like if I represent it graphically in my drawing? Right? It's a vector, so it's drawn with an arrow. How do you draw it in a picture like this, where you have an xy plane, and you've got a trajectory or a path, and you've got a position vector r1 and a position vector r2. Here's how you draw the displacement vector delta r. It's an arrow that points directly from point 1 to point 2. So that would be like that. Note the arrowhead points from 1 to 2, and then you label it delta r arrow. And that's the displacement vector. It points from the initial location to the final location. Okay? All right, we're going to end up practicing with displacement, but there we have it in two dimensions. You've got to deal with components and unit vectors and all that good stuff. Another quantity we defined in Chapter 2 after displacement was average velocity. So let's do that now for two dimensions. Average velocity is the same definition it was in Chapter 2. Displacement divided by corresponding time interval. But now we just have more complicated notation. V average arrow, now you must draw the arrow on top of the V average, is delta R arrow divided by delta T. Displacement vector divided by the corresponding time interval. But wait a minute. We already have an expression for delta R arrow. It's right there. Delta x I hat plus delta y j hat. So divide that by delta t. And you have this formula, which is very handy for calculating the average. take delta x divided by delta t and multiply that by I hat, plus delta y divided by delta t times j hat. Let me just point out, by the way, since the definition of average velocity is displacement vector delta r arrow over delta t, whatever direction delta r arrow has, that's the direction v average has. Okay? So v average has the same direction as delta r for a given time interval. So whatever direction the displacement's in for a given time interval, that's the direction of v average. For example, in my drawing here with the squirrel, we had a displacement from t1 to time interval, from t1 to t2 with a displacement delta r arrow there drawn in red. Note the direction of delta r, that's the direction of v average. So if you wanted to sketch v average for this picture, you could just draw an arrow right beside the delta r. The key thing about it being that it's the same direction as delta r. Don't draw it as the same length as delta r, because v average and delta r have completely different units. But it's got to be an arrow pointing in the same direction as delta r. Okay, so now we have position, displacement, average velocity in 2 dimensions. Ready to go on? Next thing we did in Chapter 2, after average velocity, we defined instantaneous velocity. So let's do that now. Okay, now we have a new picture. Instantaneous velocity, just as in Chapter 2. It is the limit of the average velocity as the time interval approaches 0. Exactly how it was defined in Chapter 2. And that means its derivative, just like in Chapter 2. It's the derivative of the position with respect to time. Remember, derivative also means rate of change, so you'll hear people say that instantaneous velocity is the rate of change of position. But we knew that from Chapter 2. Now we just have 2 dimensions to deal with. So v arrow, we must draw the arrow symbol over the v, is the limit as delta t goes to 0 of delta r over delta t, and that just means do the derivative. Do the derivative of r with respect to t. Now, I'll give you a little bit of a shortcut thing to note. What that really means to do is, because you got to deal with components, do the derivative of the x-coordinate with respect to time and multiply it by I hat, plus the derivative of the y-coordinate with respect to time and multiply it by j hat. You have to do those 2 derivatives. And note, the derivative of the x-coordinate with respect to time, dx over dt, is by definition the x-component of the instantaneous velocity, denoted v sub x. And the derivative of the y-coordinate with respect to time, dy over dt, is by definition v sub y, the y component of the velocity. Okay? So let's look at this little sketch that we've got in the picture right below. We've got an xy coordinate system, and where the xy axes cross is the origin O, and we've got a particle moving along some path. The particle is that blue disk, and we took a snapshot of it freeze at a certain moment while it was moving. Okay? And we are sketching its 2 velocity components and its actual velocity vector in this drawing. The full velocity vector is the red arrow with the open tip, and then the components are labeled Vx and Vy. And here's the key thing. The magnitude, first, of the instantaneous velocity is called instantaneous speed. That would be the magnitude part of v. I could denote that over here. Put the v arrow symbol in absolute value, within absolute value symbol. That means the magnitude. The magnitude of the instantaneous velocity is called the instantaneous speed. That is merely how fast the particle, I meant that to be highlighted. There we go. How fast the particle is moving at instant t. Just how fast, in meters per second. And the direction of the instantaneous velocity is always going to be tangent to the particle's path or trajectory and in the direction the particle is moving. So they're trying to show you here in the drawing the tangent to the path at the moment in question, right here, and the velocity vector is along that tangent, because that's the direction the particle is moving at that instant. Okay, so same definition of instantaneous velocity as we had in Chapter 2. We just have two dimensions now. Okay, now that I've introduced position, displacement, and velocity, both average and instantaneous, in 2 dimensions, let's do them all again in 3 dimensions, because there are objects that will move around in full 3-dimensional space. So now, and of course, there's a challenge when you want to represent 3-dimensional motion. You have to do it on a 2-dimensional surface, whether it's a piece of paper, or a whiteboard, or a chalkboard, or a computer tablet. You've only got 2 dimensions to work with, but you're trying to represent 3 dimensions, or motion in 3-dimensional space. And it gets a little tricky, so you have to kind of practice a bit, getting used to it. Okay, so here we go. First, we'll start with position in 3 dimensions. Well, it's the same idea. It's a vector pointing from the origin to the particle's location at an instant in time. And so, here I've drawn, or here I have a sketch of a particle, and it may be moving around, but we took a snapshot in time, freeze, and there's where it is. You see the green looks like a kind of a sphere. That's our little particle. And to denote for you where it is, one of the things you probably could imagine doing is giving you its 3 coordinates. That's telling you where it is. X and Y and Z. And if I tell you that X is -3 meters, and Y is +2 meters, and Z is 5 meters, then that tells you where the particle is, yes? You go -3 meters parallel to X, and then +2 meters parallel to Y, and then +5 meters parallel to Z. And that's what this picture does. And it takes the X and the Y and the Z and it multiplies each of them by their corresponding unit vector to get 3 vector components. Let's draw them. And that gives us the position vector, R arrow. Because R arrow is X times I hat plus Y times J hat plus Z times K hat. So let's sketch those in the picture. They're sketched. I'm just going to emphasize them. Start at the origin. Let's do the X component first. -3 meters times I hat. So go 3 meters in the negative X direction, right here. Okay? There's the X scalar component of the position. -3 meters times I hat. Now just pick up from there and go 2 meters parallel to Y. 2 meters J hat. That's that arrow right there. And then, going from there, go 5 meters parallel to Z. 5 meters K hat. That's it right there. Then add those 3 vectors. Vector addition, draw an arrow from the tail of the first to the head of the last. And you'll note then that that vector will point from the origin out to where the particle is located. And that's the position vector, R arrow. Here it is for this actual example I'm doing with you in unit vector notation. -3 meters times I hat plus 2 meters times J hat plus 5 meters times K hat. Okay? So it's important that you see how writing the expression for R hat in unit vector notation translates into the sketch of showing where it actually is. And now what we have, by the way, is an XYZ coordinate system with an x-axis pointing to the right on the screen and a y-axis pointing upward in the screen And then this z-axis, you're supposed to imagine that coming directly out of the screen towards you. Okay? That's our way of representing 3 spatial dimensions on a 2-dimensional surface. Now, suppose this particle is moving around. And so, at some later time, it could be at a different location. So its position vector will change. So it will have a displacement. Delta r arrow. How would we calculate that vector, delta r arrow? It's easy. Just take the change in its x-coordinate times I hat, plus the change in its y-coordinate times j hat, plus the change in its z-coordinate times k hat. And yes, there'd have to be enough information in the problem to actually calculate numbers for delta x and delta y and delta z. Then how do you calculate the average velocity of the particle? Let's say the displacement delta r occurs in a time interval delta t. Then just take delta r arrow divided by delta t. And in unit vector notation, that just means take delta x divided by delta t times I hat, plus delta y divided by delta t times j hat, plus delta z divided by delta t times k hat. And what about the instantaneous velocity of the particle? How fast and in what direction is it moving at any given instant? V. That is the derivative of the position vector with respect to time, dr arrow dt. But you just write it out by components. dx by dt times I hat, plus dy by dt times j hat, plus dz by dt times k hat. And, by the way, dx by dt by definition is v sub x, the x component of the velocity. dy by dt is by definition v sub y, and dz by dt is by definition v sub z. All right, I think it will be helpful, maybe, for you, if I do a little mini example. Okay, so I'm going to do that next. Last thing I do on this video. A little mini example, okay, in which I'm going to show you a little bit how you practice with this. What I've done is I've taken a Wiley Plus problem from the end of chapter 4 that's a little bit more on the basic straightforward side, just to show you how you do these kinds of calculations. Let's suppose we are given the following, that a particle has a position vector, position, r arrow, that's going to be given to us in unit vector notation. Here we go. 3 times t times I hat plus negative 4 t squared times j hat plus 2 times k hat. Okay, so we're given the position vector in unit vector notation. I see that the x-coordinate of the particle, which is the thing multiplying the I hat, depends on time. That, right there in parentheses, is x of t. The x-coordinate is a function of time. What are the units of the 3, by the way? We're assuming r is in meters and t is in seconds. You might want to think about that a minute. Okay, now, if the t is in seconds and the r must be in meters, 3 times t, which is x, must be in meters. So 3, just the 3, must be in meters per second. You need to think about that maybe a little bit, okay? All right, next, the quantity multiplying j hat, negative 4t squared. That's the y-coordinate as a function of time, right? It's got a t in it. And then lastly here, the quantity multiplying the k hat is the z-coordinate. And I'll just denote that with a z and no t because there is no t, right? That means I know the z-coordinate of the particle is constant at a value of 2 meters. Here's what I'm asked to find. Find the velocity vector as a function of time in unit vector notation. I'm going to just do it component by component. It's really the only way you can do it. That is to say, to get the x component of the velocity, I will take the derivative of the x coordinate with respect to time, dx by dt. What's the x? 3t. So you just have to be able to do the polynomial derivative, the derivative of 3t with respect to t. And you need to practice with that perhaps, but the answer is, if x is 3t, then the derivative is 3. So that's v. And if I were to put specifically the units, at least for right now, it's meters per second. That's v sub x. To get the y component of the velocity, v sub y, we take the derivative of the y coordinate with respect to time. The y coordinate is marked right up there, negative 4t squared. What's the derivative? dy by dt. Maybe you should pause the video and think about that. Feel free to do so. Okay, did you try the derivative dy by dt for yourself? If y is negative 4t squared, the derivative dy dt is negative 8 times t. That means the y component of the velocity depends on time. It's changing. Is that true for the x component of the velocity? Is it changing with time? No. There is no t in the expression for v sub x. It's constant. But v sub y changes with time. All right, still got a third component to worry about. The z component of the velocity, v sub z. That is found by computing dz by dt. Okay? If you need to pause the video, that's fine, but I want you to think about that for a moment and get an answer. What is dz by dt? Okay, did you say dz by dt is 0? Because z is constant, 2. And the rate of change, that's what dz by dt is, of a constant is 0. So there is no z component of the particle's motion. It's got an x component of its velocity and a y component, but it doesn't have a z component of its velocity. So the final answer, we're not quite done, for the velocity as a function of time is, take the expression for v sub x, for brevity I won't write the units, so 3 times I hat plus, now v sub y, negative 8t times j hat. And mark your answer. There's the velocity as a function of time. You tell me the value of t you're interested in, I will plug in and tell you v at that t. Okay? So it's not complicated, you just have to get used to the terminology and the notation. Okay, that is all for this video lecture.